Did you delete the other one?
Mm-hmm.
Okay.
Action.
Well, I'm just going to briefly mention randomized algorithms. The basic idea of a randomized algorithm is that instead of having a deterministic choice, a deterministic decision at every step, you can imagine throwing dice or whatever to choose an outcome. Now there are classically two kinds of randomized algorithms: Monte Carlo algorithms and the more recently found Las Vegas algorithms. Now Monte Carlo algorithms take a fixed amount of time, but they give only usually an approximate answer, and the answer is, on the average, fairly close, at least if you do it right, fairly close to the correct answer, but there's always a small probability that it's far off. Now, quite the opposite of that is the Las Vegas algorithm, which always gives the correct answer. If the algorithm is correct, it always gives the correct answer for sure, but the amount of time it takes is quite uncertain. For example, in the algorithm I'm going to show you for the median problem, the expected time is O of n, but the worst case time is O of n squared, although that's very unlikely. Now I'm going to introduce the problem of finding the kth smallest item in S. Now this is a generalization of the median problem. The median problem would be to find the n over 2, the smallest item in S, where n is the size of S. However, it turns out that we have to use this more general term, which is sometimes called order statistics or rank, but I'll just call this function find. Now, to execute find ks, you have a set S which has n elements, and an integer k which has to be something between 1 and n. And the output of this is the kth smallest item in the set S. Well, there is one very simple-minded, obvious way to solve this problem, and that is to first sort the set S. That goes into an array, let's say. You just reach in and pick the kth one in the array. Now, of course, you have to sort, so that takes O of n log n time, since we are using the comparison model. And of course, picking the kth one just takes one step. So O of n log n is the time complexity of this simple-minded algorithm. Now, the pivot method, this is very general, and it covers the other things we'll do. The pivot method is to first pick a pivot which is a member of the set S. Now, we're not going to discuss right now how we pick the pivot. That will be done somehow, either using randomization or some other deterministic way. But let's say we have already picked the pivot. Then we partition S into two sets. We'll call S1 and S2. S1 would be the smaller ones, those that are less than or equal to the pivot. And S2 would be all the ones greater than the pivot. Now my question to you is, how long will it take to execute partition? Partition can be executed, obviously, since I will have to look at each element at least once, it takes O of n time to execute the partition. All right, after you've done the partition, we look at the comparison between k and m, where m is the number of items in the smaller set, the set of smaller elements. We'll call that m. So m is less than or equal to n. Now, if k actually is equal to m, then we have found the kth smallest. That's it. It's p. We're lucky. More likely, it's smaller or larger. If k is smaller than m, then recursively we return the value of find k s1. Since s1 is a smaller set than s, well, actually, we're not going to use all of s1 here. We're going to subtract the pivot element. So actually, it'll be definitely smaller than n in size. And then if k is greater than m, then we find the k minus mth member of S2. We could draw a little picture of this if we want. If we think of them stretched out like this, the pivot here and S2 there, if we're looking at k, if k is in this range, then the kth element of S is the kth element of S1. But if m is in this range, then this is the kth element altogether, but we have to subtract m as an offset to get its position within S2. Now the only remaining question is, how do we select the pivot? I've shown you how to do the recursion and how to do the partition. The partition is actually very simple. How do we select the pivot? Well, there are two ways. One is using randomization, and the other is deterministically using the median of medians algorithm. Now, when we do randomization, all we do is pick the pivot to be an arbitrary randomly chosen member of the set S, presumably with a uniform distribution, so each element of S is equally likely. Now, when we do that, then on the average, the pivot we choose is not too close to the edges. Too close to the edges means it doesn't split very well, which tends to make the algorithm go longer, but a good portion of the time it's not too far. It's sort of roughly in the middle. And so on the average, it converges in only log n recursive calls, approximately, actually O of log n recursive calls. And each recursive call costs O of the size of the set we're using now. So the recurrence we get in the case of a randomization is f of n is equal to f of some small fraction of n, let's say n over something, plus n. Now, where a is some number which is larger than 1, and so therefore, on the average, this works out to be theta of n using the master theorem. Now this is of course a randomized result, namely this is only what the average is. So the average is theta of n, but the worst case is theta of n squared, because we could have an n minus 1 split every single time. All right, now the next thing to try is the deterministic method, which is actually somewhat complicated. I'll erase this to get that out of mind. We pick P to be the median of medians. Now, I'll explain what that means in the next slide, but we're going to pick a P which is actually in a sort of middle interval. This picture shows you, suppose that this represents the set S, and this represents the point 3n over 10. In other words, the 3n over 10th smallest member, and this is the 7 over 10th smallest member. So this distance is 3n over 10, this is distance is 3n over 10, n over 10, and this is everything else. And we can deterministically force the P that we pick to be in the middle section, which basically means that it will converge using the generalized master theorem, which I've shown you before and which we'll go over again. All right, now the step goes like this. This is the median of medians method of choosing the pivot. First, partition S into blocks of size 5. Now, actually, since n might not be a multiple of 5, there'll be a block left over, which is of size 5, 4, 3, 2, or 1. I drew it as 4. Now, you sort each block. Now, why does that take O of n time? There are O of n blocks, and each one takes finite time to sort. It takes no more than maybe 7 comparisons to sort a set of size 5. And so we do that. It might be 8 comparisons, I forget, but it isn't much larger. So once we sorted them, we then can pick the set of medians in each block. There's the middle element, the third element in each block. And I'm coloring that red in the figure. Now, once we get this set, how big is it? Answer, n over 5, because I have n over 5 blocks. Then I let the pivot element be obtained from a recursive call to find the n over 10th smallest member of M. And that is, of course, the median of M, because M has n over 5 elements. Now we'll show the other properties in the next slide. All right, now what we're going to do is, first of all, I'm going to rearrange the blocks. So in the middle of the picture, I'll put the block that contains P. And then, while I partitioned the blocks, I moved them around. So all of these positions, the medians, are less than or equal to P. And on this side, the medians of these elements are greater than or equal to P. Now, you notice I'm only talking about the median of each block. So the other elements could be something else. Now, what I'm going to do is I'll consider all the blocks whose medians are less than or equal to P. And I will take a set T, which is all these boxes, all the elements that are less than or equal to the median of each block, which is on the left side of the middle block. Now, I want to tell you that all of these block elements are less than or equal to P, because the largest one in here is P itself. All the rest are, every one of these medians is smaller than or equal to P, and every one of the things to the left of one of the medians is less than or equal to that. So therefore, I conclude that the size of T is less than or equal to 3n over 10. Now, how did that come about? Well, they're n over 5 blocks, and they're roughly n over 10 blocks on the left side, and for each one of them I get 3 elements. So 3 times n over 10. That's the size of T, which means that there are at least 3n over 10 elements smaller than P. Now, how many elements are there larger than P? Well, we can do the same thing on this side. If there's no element equal to P, then the number of elements larger than P is greater than or equal to also 3n over 10. All right, now once we picked that partition, we proceed as before. All right, now, when we partition in 2 sets, S1 and S2, each of the 2 sets has size at least 3n over 10. And each of the complementary sets has size at least 7n over 10. Now, the 7 over 10, when we do the recursive call, it will be on one of those 2 sets. The worst case is it's the larger one, and the larger one could have size up to 7n over 10. So, when we execute the find algorithm, we're going to recursively call it with n over 5, then again recursively with no worse than 7n over 10. And now you notice that 1/5 plus 7/10, which is 9/10, is less than 1. And by the generalized master theorem, which I've told you, T of n is thus equal to theta of n, and that's deterministic. And hence the algorithm works deterministically in theta of n time.